So here is some of the code. Of course, you can just go on GitHub and clone the repository and try to better understand it yourself. I think I documented everything quite well, but here is the brain of the tool, the ODE solver script. So I use Python's SciPy package, which is a well-established Python package to do science-related stuff. And specifically, I use the solve IVP method in this package, and it's responsible for solving ordinary differential equations. The challenge was I had to make it work with multiple bodies, and so I had to make it such that you're able to input a array or a set of conditions that accounts for any possible number of bodies that the user wants, be it 3 or 20. And this came with a bunch of challenges, but that means essentially I had to do a nested for loop system. And nested for loops are incredibly annoying because they're often extremely hard to optimize, and they sometimes function so much slower than you want them to be. I managed to get it to work after reformulating and remaking the structure of the code. And this is the solution that I'm using right now. To show the basics, let's take a look at the original code that I used to mess with two-body systems. Here I used ODEs, but it was for only two bodies, so it was a lot simpler. I used the solve IVP method, and it takes in another function, which is a ordinary differential equation written in code. This is Newton's law of gravitation, and this part is responsible for calculating everything. The solve IVP function is what does the iteration, and it repeats for however many iterations that is determined by a lin space somewhere else in the code. Since I'm solving a second order three-dimensional differential equation, the ODE solver takes in 6 position values for the XYZ dimensions of the two bodies and 6 velocity values for the XYZ velocities of the two bodies. As for the calculation part, it returns the velocity and acceleration values, or the first and second derivative. The calculation function determines the relationship between the values of the second order differential equation, and solve IVP then uses these to simulate the system, utilizing the fifth order Runge Kutta method. This solving is repeated a bunch of times until every data point is generated. Now, you might be asking, what's the difference between this approach and other methods like Euler's method for solving ODEs, or simply iteratively using kinematic equations? I was asking myself the same question as well initially. The answer? Well, it's just better. Okay, but seriously, it's because ODE solvers like this fifth order Runge Kutta method are more efficient. Euler's method is still an ODE approximating technique, but it's a first order approach. It approximates the future values based on a initial position and only does it based on the first derivative of the function, which is much less accurate than a fifth order Runge Kutta method used by SciPy. As for a kinematic approach, you're calculating the gravity and change in position for every single time step, which is very computationally intensive. Even if the values aren't really changing much, you're effectively doing a bunch of redundant calculation for no reason, and therefore this method can be incredibly slow. This ODE solver numerically integrates based on how much the function is changing. It dynamically adjusts the step size, and the step size will increase if the values aren't changing that much, so it massively reduces computational load while still retaining accuracy. Now, to make it work with multiple bodies, it simply was just summing all the accelerations together with the nested for loop. Another important thing is the normalization function. Since the units by default are in AU, floating point errors become exaggerated when I have smaller distances like Earth and the Moon. I don't have a plot for it, but when I tested it, the orbits kinda looked like this. Sometimes they simply wouldn't run. I had to do some normalization because without it, there would be a lot of floating point error, and large scales and number ranges cause huge inefficiencies and redundancy in computation, which would make it really slow. Essentially, instead of the base unit being 1 AU, the base unit is now the smallest distance that exists within the simulation. So, for instance, the Earth and the Moon, there being a very small distance, that distance will now become the base unit. Obviously, there are some more details that you can check out by reading the code in the GitHub, but these are essentially the main parts of the code that I think are worth talking about. And in the next video, I'm going to talk about the accuracy and the speed of this tool. Thank you for watching.